Hey everyone, welcome back to Abstract Algebra 1. This is going to be part B of lecture 11. And in this section, I want to start by jumping into a really great example of factor and quotient groups. And so I would think of this as kind of a critical example, only because it's so good at generating intuition about these rather abstract ideas. Right, and so this is going to be a critical example taken from the dihedral group D4. So recall D4 is the group of rotations and flips of symmetries of a square. So R0, R90, R180, R270, a horizontal flip, a vertical flip, and two diagonal flips. Right, now we're going to consider a subgroup K. And K we're going to make R0 and R180. Now, K is normal. K is normal in D4. It's a normal subgroup of D4. Okay. Now, what I want to do is I'm going to spend a little time developing the cosets of K just to make sure that that idea is clear. Right? Because I think when we get to the Cayley table, if we have a good sense for where the cosets came from, it'll really help make the connection clear. All right, so what are the cosets of K in D4? Okay, and so what we want to do is we want to think about the elements that are in K. And we want to think about what happens to the set K when we compose it. In this case, the operation is composition. When we compose it with all of the elements in the larger group D4. Okay, so let's start with R0. R0 of K. Well, that's just R0, R0, right? So composing R0 with all of the elements of K, you get this. Let me make sure this is focused here. Right? And so this, of course, is R0, R180, and therefore, obviously, it's just K. Right? And we kind of should anticipate that, but let's just make sure we see it. And the same thing is true with R180. So R180, R0, R180, R180. Of course, that's R180, R0. So again, K, right? These are the same, right? So the first coset number 1, is just R0, R180. And we're going to denote the coset as K, namely the name of the normal subgroup of interest here. All right, so that's coset number 1. Now let's move forward. So we've exhausted 2 of the 8 elements. So we took a look at R0 and R180. Let's look at R90 next. R90, composed of K, is, let's write it out, it's R90, R0, and then R90, R180. Right, and we know that that's going to be R90, and then what's 90 and 180? 270, right? Okay. All right. Now I have a hunch that R270K might give me the same answer. Let's check it. Right, and you do see that R270 R0 is R270, and R270 180 is R90. Right, so these are the same. Now, if you just went through and just did all of the others, you'd notice that the diagonal flips and the horizontal flip and the vertical flip, they aren't the same, right? So I'm just going to cut off the investigation here and say that coset number 2 must be this. Right, so coset number 2 is R90, R270. Now we can name it R90K or R270K. Let's just go with R90K. We need to give it a name, so let's name it this one. It doesn't matter which way you name it. It just whatever seems right to you, whichever is more convenient. And so we'll go with 90. Okay, so coset number 2 is this. Now let's look at the horizontal flip. So HK. So what is that? That's HR0 and HR180. Well, you can let's look at it. Let's just be really careful here and make sure we can. So sorry, 0 and 180, right? Yep, 0. Okay. So let's look at HR0 first. I'm going to actually do the derivation using the actual symmetries. Okay, so this is HR0. So if I start with 1, 2, 3, 4, and I do an R0 on that, of course I get 1, 2, 3, 4 unchanged. And if I do a horizontal flip on that, I get 3, 4, 1, 2. Okay, and so that's really just H, isn't it? And that's just the same as doing a horizontal flip. What about H R180? Again, 1, 2, 3, 4. Let's do an R180 on that. Right, and I get 4, 3, 2, 1. Then let's do an H on that. And when I do that, I get a 2, 1, 4, 3. Okay, and that's equal to V. Okay. Right, so these are the two elements of HK. Right, and so that tells me that this is going to be H and V. Okay, let's look at V. I have a feeling that V is going to work here as well. Right, so let's look at VK. So VK is going to be VR0 and VR180. And what does that equal to? Well, again, we're going to go through this. We're going to look at VR0. And so if I start with 1, 2, 3, 4, and I do an R0, I get 1, 2, 3, 4. And then if I do a V, a flip along the vertical orientation, I get a 2, 1, 4, 3. And so that's just V. Right, what about V180, R180? Well, again, 1, 2, 3, 4. I'm going to do an R180 on that. And when I do that, I get 4, 3, 2, 1. Right? So 4 goes up here, 3 goes up there. Remember, everything is just rotating 180 degrees. What happens if I do a V on top of that, a flip along the vertical axis? Then I get a 3, 4, 1, 2. Okay. Now a 3, 4, 1, 2 is really just the same thing as an H. It's a horizontal flip, isn't it? So look at here. These two are the same, and these two are the same. Right? So that tells me that VK is V and H. Right? So I've got HV and VH, so that means HK and VK are in the same coset. Right? So that tells me what coset number 3 is equal to. Okay. So coset number 3, hang on a second. Coset number 3 is H comma V, and we can name it HK or VK. I'm going to just call it VK. Okay, just like before we had our choice with R270 or R90, we can name it R270K or R90K. We just name it R90K. Right, so we're going to call this one VK. Okay, and we can do the same thing for the last two elements. We can do the same thing for the last two elements, right? What we would see is that dk is equal to dr0, dr180, and this, you'll have to pull out the square and actually check it, but you'd see that this is d and d prime. And then d prime k is d prime r0, d prime r180, And here again, you would see that this is d prime d, right? These are the same. And so coset number 4 is d prime, and we can call it what we want, dk, d prime k. I'm going to call it dk. Okay? All right? So we've got our 4 cosets of d4. Let me enumerate them here. So the 4 cosets are R0, R180, and then it's R90 and R270, and then it's V and H, and it's D prime. Okay, this one we're calling K, this one we're calling R90K, this one we're calling VK, and this one we're calling DK. And these are just names. Okay, just names. Okay, now the next thing to do is we want to go back and look at the Cayley table for D4. All right, we want to look at the Cayley table for D4, and you'll have to bear with me. We've done this before, so if you have your notes from previous lectures, you don't need to obviously do this again, but we've done this one before, and it's just going to take a second for me to write it out. I want to make sure to write it out here. So what we're going to do differently, though, is we're going to organize the Cayley table by the cosets. Now, all that means is that I'm going to put columns next to each other if they're in the same coset. So I think originally I would have gone R0, R90, R180, R270, but this time I'm going to do R0 and R180. I'm going to put them next to each other. And I'm going to do R90 and R270 together, and V and H together, and D prime together. Right, and that's just going to make the structure pop out a little more and make it clear what's going on. All right, so we've got R0, R180, R90, R270, H and V, and then D and D prime. Right, and so the cosets are separated here. Okay, and then across the top I'm going to do the same thing, R0, R180, and then R90, R270, H and V, D and D prime. Okay, and so this is the Cayley table. This is what it looks like structurally, right? Just organized in this way. Okay, so hopefully this is nothing too crazy yet. All I've done is swap the columns out a little bit. Okay, again, this is the same table as before. I highly recommend that you do redraw it simply because the structure is going to look a lot better when you have the columns in the same orientation. Right, now if we just go through and we just fill this out in the normal way, so an R0 and an R0 gives you an R0, an R0 and an R180 gives you an R180. An R180 and an R0 gives you an R180. An R180 and an R180 gives you an R360, which is an R0. Right? Just going through, and you can fill out all of these, not doing anything special, just literally looking at the two elements and saying, what do I get from that? Right? What's an R0 and an H? It's an H. What's an R0 and a V? It's a V. What's an R0 and a D? It's a D. R0 and a D prime is a D prime. Just kind of go through it, right? Now you can do it this way, which is fine, but I think what's more interesting and what kind of pulls out the structure here a little bit more is if you kind of do it square by square. So R0, R180, R180, R0, we did this square. Now it turns out that these same elements appear here next, right? And so here you get an R180, an R0, an R0, and an R180. Okay, and then down here you get an R0, R180, R180, R0, and then the same thing down here. Okay, so you're already seeing a structure pop out of this, right? So you've got all of the K's together, right? So this is basically the this is the coset with, this is the coset that we named K, right here and here and here and here. Okay. Now, just going through and kind of filling in the rest of this, R270, R90, V and H, D prime and D. Okay. Now, I'm not going to fill in the rest of them yet because I want to jump to the Cayley table for D4 mod K. And then what we're going to do is we're going to use that to predict what goes where here. And you'll see that it works out exactly right. So what about the Cayley table for D4 mod K? Well, we're going to do the same thing. We're going to have our K, and then R90K, and then HK, and then DK, right? And then along the top, the same order matters here. R90K, HK, DK. Okay. And so a K and a K gets you what? So first of all, let's remind ourselves what it means when we combine these things. So for example, if I want to combine an R90K and an R90K, what does that mean? Well, remember the group operation says take the two front things and put them together. So you get like an R90, R90K, right? Which is an R180K, which is K. K absorbs 180, R180, right? And so R90K, R90K, this intersection should just be a K. Okay, now let's look at what this cell represents in the Cayley table of above. Right, so this is the R90K and this is R90K, and look, you see K is there. Right? What about HK R90K? Well, we know that that's HR90K. And what is HR90? Let's try to remember. Well, you could do it from first principles. So 1, 2, 3, 4, do an R90, and you get 2, 4, 1, 3. Do an H, and you get 1, 3, 2, 4. And you can see that HR90 is really just a diagonal flip. 1 and 4 are fixed, and 2 and 3 swap spots, right? All right, so this is just DK. Okay, so HK and R90K, so basically here and here, this better be a D. DK. Let's go upstairs and look here. Well, we didn't fill it out, so let's fill it out. What's H and R90? Well, H and R90 is a D. Right, we just did that. Right, that's basically what we did right down here. HR90 gets you a D. What's a V and an R270? Well, you can spend a little time, but you'll see that that's a D. What's H and R270? That's a D prime. And V and R90 is another D prime. Right, so this is DK, as we expected. Okay. Right, now over here, HK and HK, that's a K. DK and DK, that's a K. K and K, that's a K. So there's where you see the K's along the diagonal. Right, and you've got that here. Here's K, there's K, K, and K. All right, let's fill in the rest here. R90K and a K is an R90K. K and R90K is again an R90K. HK and a K is HK. DK and a K is DK. Right, now notice HK and DK. There's HK. There's DK. Right, you see the structure? It just collapses down. Right, DK, HK are here, and so this is going to be D prime D, D, D prime, and then this will be H, V, V, H. Right, so you can see that DK, HK, DK, HK. Now what is this guy going to be? Well, let's look down here. HK and a DK. What do you get when you combine HK and DK? Well, you just have to do the same thing that we did below here, but what you'd find is that that's an R90K. Right? So that means up here, I better get R90 K, right? So that's an R90, R270. Just remember what's in that coset, R90K. It's R90 and R270. Right? And you can confirm this. H and a D better give you an R90. A V and a D better give you R270. And it does, right? So these tables just collapse down, right? So let's fill in the rest just so you can check this. R90, R90, R270, R270. And here I get HV, VH. Here I get D, D prime, D prime, D. And then V, H, H, V. And then the last one here, R270, R90, R90, R270. Right? So this is the Cayley table for element-wise inside of D4, right? Organized so that the cosets are together. Right? So this is K, this is R90K, this is HK, this is DK, right? And the same over here, right? So each of these squares represents the intersection of the cosets, or the result of the cosets operating on one another, right? And then down here is explicitly writing out the cosets. So here I get HK, and here I get DK, and HK, and R90K. Right? And you can see that this structure collapses right onto this smaller table. Okay, and so that's a fantastic example to look at just from the ground up. Take a group that we're very familiar with, we've looked at it, we've developed it, and look at the Cayley tables and how one collapses onto the other. Okay, all right, we can see that basically the formation of the factor group, the formation of G mod H, in our case D4 mod K, it basically causes a systematic collapsing of the elements of the group D4. Causes a collapse of D4's elements. All right. Okay. So so basically all of the elements in the coset collapse into a single element in the factor group. Right. So all the elements in a coset collapse down into a single element in factor group. That's amazing. That's amazing. Okay, amazing structure. All right, very good. Let's go ahead and round out this lecture. We've got a few items to discuss. So there's a range of theorems that can give that. There's lots and lots of theorems that aren't going to be stated here, but there's a couple theorems I want to at least write out so you can begin to think about the kind of information that factor groups can give us regarding the group. Right, so there's 3 of them, and I'll write them all out. I don't think we're going to prove any of them, just in the interest of time. But the first one says, let's let G be a group, and let ZG be the center of G. Okay. If G mod ZG is cyclic, then G is abelian. Right? So if I have a group G and I can easily identify the center of G, then I can determine whether or not G is abelian by whether or not G mod ZG is cyclic. Right? So that's interesting. It tells me something about the larger group G just based on the factor group GZG. Okay. Here's another one. For any group G, G mod ZG is isomorphic. It's isomorphic to in G, right? This is the inner automorphisms of G, right? And so what about in G? Well, so in G, the function says phi sub a of x is equal to ax a inverse for all x in G. This is called the inner automorphisms of G. And technically induced by A. Okay, so we saw this before, but basically, so this is just saying that for any group G, G mod ZG is isomorphic to this inner automorphism group. Okay. And then finally, and again, these are just, we're going over these quickly. The goal here is just to get you thinking about. I wouldn't expect you to like master and memorize these from just the statement itself. But the third theorem says let G be a finite abelian group. Let G be a finite abelian group, and let P be a prime that divides G. That divides the order of G, sorry. Okay. Then what this implies, then G, the group G, has an element of order P. Okay, so if G is a finite abelian group and P is a prime that divides the order of G, then G has an element of order P. Okay. All right, and so this theorem here is going to rely on factor groups. It doesn't actually use factor groups in the statement of the theorem, but factor groups and factor groups are a big part of the proof of this theorem. Okay. All right. Okay, very good. And so we're very near the end. I want to just touch briefly on one other concept quickly here. And this last concept is the concept of an internal direct product. So we've seen external direct products. Right, and external direct products are, they give you a way of putting groups together into a larger group. Putting groups together into a larger group. Right, and so we saw examples of this: G1 plus G2 plus ... plus Gn, where all of the GIs are all individual groups, and you can compose a larger group out of them. So now what we'd like to do is kind of reverse the process a little bit, or you can think of it that way. With an inner direct product, we can start with a larger group and break it down into a product of smaller groups. So an internal direct product starts with a larger group and collapses, breaks it down into a product of smaller groups. Okay. And so to explore this idea, what we're going to need is we need the following. Let's define the set. And define the set HK. Well, so define the set hk equal to the set of all the products of h and k such that h is in a subgroup H and k is in a subgroup K, where H and K are subgroups of G. Okay, so I've got some group G, and H and K are subgroups of G, and then I define this set HK. Okay. So a simple example just to make sure that we understand this idea. So given here's U24. I'll write it out. Wouldn't be simple if you had to figure out what it was, but 1, 5, 7, 11, 13, 17, 19, and 23. Integers under multiplication, mod 24, that's this guy. And let's let H equal 1 and 17, and K is equal to 1 and 13. Then HK is equal to 1 times 1, which is 1, 1 times 13, which is 13, 1 times 17, which is 17, and then 17 times 13, which turns out it's a big number, but if you multiply that together, you'll see that it's 5 mod 24. And this is, again, 13 times 17. Okay. So that's just an example of this HK set, right? So it's really just you multiply everything together, or the operation of the group G and the subgroups H and K is really what you're doing here. In this case, it's multiplication, mod 24, but it could be addition, or it could be regular multiplication, or multiplication by a different modulus, whatever it happens to be. Okay, so then definition. Here's the internal direct product. So we say that G is the internal direct product of H and K, and we write G is equal to H, we write it like this, times K, if H and K are normal subgroups and G equals HK, right? So namely the group you get when you multiply everything together gives you G, and H and K have only the identity in common. So H and K are basically disjoint except for the identity. Okay, so this is what we mean by this is the definition of an internal direct product. So G, the group, can be called the internal direct product of two subgroups of itself if the two subgroups are normal, and G, the group itself, is equal to the product of all of these elements, and H and K happen to be, have only the identity in common. All right, so what the heck is this? Let's talk about this for a second. This is a very interesting concept, and it aligns well, it really is the same idea as the external direct product. So G is the internal direct product of H and K. It's the internal direct product of H and K, right? If H and K are subgroups of G, and G is, so if H and K are subgroups of G, and really what we mean here, and G it's got to be isomorphic to what you would think of as the external direct product of H and K, right? So when we say internal, what does that really mean? It means you start with groups inside the group. You start with groups inside the group, and you end up with G isomorphic to basically an external direct product of the two subgroups, right? But the key is you start inside the group. And contrast that with the external direct product. You start with any group in the world, right? And really, you start outside of G. Like something like this, right? So the key is outside. The internal direct product starts with subgroups and develops, identifies the two subgroups or more, and such that combining all of the elements gives you a group that's isomorphic to G. Okay. External direct product is the same idea, except there's no constraint on where the groups G1 and G2 come from. They don't necessarily have to be subgroups of G is the key point there. Okay. Okay. And so you can think of it like this. If I have some group G, the identity's in there somewhere, right? And then I've got some subgroup H, and I've got some other subgroup K, and G needs to be isomorphic to H direct product with K. Right? It's really the same idea. Take some subgroup H, some subgroup K, generate the external direct product of the two, and you have generated an internal direct product. Let's do a couple of examples here to wrap it up. Right? So this is an interesting idea, right? Representing a group using a combination of other groups, but with the constraint that the groups, the combination groups, have to come from within. Right? So let's consider Z6 for our example. So Z6, of course, 0, 1, 2, 3, 4, 5. Right? Modulo 6, addition under modulo 6. Right? And let's think about a couple of elements in Z6. So let's think about 3, and the subgroup generated by 3 in Z6 is 0 and 3. If I add another 3, I get 6, which is back to 0. If I add another 3, I get 3, and then another 3 gets me 6, back to 0, right? And then the other subgroup of interest here is 2. And of course you get 0, 2, and 4 there, right? So I've got two subgroups of Z6. So 3 is a subgroup of Z6, and 2 is a subgroup of Z6 as well. Right, so they're internal. Right, now let's think about HK in this case. Right, so the HK, the notation kind of comes from the idea that the operation is a product, but here the operation is addition, so we just replace it. So it's really 3 plus 2, right, like this. So I take every element in 3 and add it to every element in 2. So what do I get? I get 0 plus 0, 0 plus 2, 0 plus 4. Right? And then I get 3 plus 0, 3 plus 2, 3 plus 4. Right? So of course this is 0, 2, 4, 3, 5, and then 7, which is 1, mod 6. Right? And so this, of course, is Z6. Right? So you can write it like this. 3 crossed with 2 is an internal direct product of Z6. Right, and you could think of it as an external direct product by just changing your notation slightly. Right, if I want to do 3 external with 2, then what is that? Well, that's just going to be 0. Right, you can write it like this. So 0, 0, 0, 2, 0, 4, and then 3, and then it'll be 3, 0, 3, 2, 3, 4. Right? And so obviously this isn't equal to Z6, and so what we would say here is that this product here, this external direct product, which is really an internal direct product because these are from inside the group, but it's sorry, I don't mean to confuse you on that. This is an external direct product, the way we set it up. This is going to be isomorphic to Z6. Right? So this is going to be isomorphic to Z6, meaning it has the exact same structure. Right? And so really this here and this here are going to be isomorphic to one another. So that's an example. One more example, and then we'll call it quits here. One more example. Let's let H equal the set 1 and 3, and let's let K equal the set 1 and 5. So then HK, H times K, internal direct product is equal to U8, right? And we can see that really quickly. So multiply everything in H by everything in K. So it'll be 1 times 1, 1 times 5, and then 3 times 1, and then 3 times 5. That's everything, right? So you get 1, 5, 3, and then 15, which is 7 mod 8. So this is 7, well, 15 equals 7 mod 8. Right, so be careful of that. Right, but this is obviously equal to U8. Right, and again, you could do the same thing using the external direct product idea. Right, so the external direct product would look like this. You'd have 1, 1, 1, 5, 3, 1, and 3, 5. And this guy here is isomorphic to U8. Okay. So one is an internal direct product, one is an external direct product. The two are isomorphic to each other and ultimately to the group of interest here, which is U8. Okay. Excellent. All right, so that is going to do it for this section. Now, next time we get together, we'll talk about group homomorphisms, and that will really be the last lecture that is explicitly a group theory lecture. So we've got one more lecture on group theory, and then we're going to move on to another idea in abstract algebra called a ring. So we'll move from groups to rings in 2 lectures. Next lecture we'll wrap everything up in group theory with the idea of a group homomorphism. All right, until then, take care.